Previously on
Michael's slow descent into insanity.
Why Vice Admiral Holdo's entire role in Episode 8 should have gone to Admiral Akbar. Master tactician, war hero, meme lord, and savior of the galaxy as a whole on more than one occasion. This is a man we have seen fighting for freedom in many stories for over 30 years. But then Rian Johnson goes and screws this all up. How can you give this absolute legend a lame as hell off-screen death, which no one reacts to in the slightest, and has no effect on anyone throughout the rest of the story?
Hello there and welcome to No Useless Questions, where today we're going to be looking at the Holdo Manoeuvre, simultaneously one of the most awesome and controversial moments in all of Star Wars, and I promise I will try my best to not go on an Admiral Akbar tangent. Before we get into it, make sure to apply an appropriate amount of force to the subscribe button to make sure you keep up to date with all the uploads on this channel. Everyone always goes on about smashing the subscribe button, but that seems like a bit of overkill to me really. So if you haven't seen The Last Jedi, this is the Holdo Manoeuvre. Basically, Vice Admiral Holdo here is apparently the first ever person to try ramming their ship through another ship using hyperdrive. Just as a quick aside here, for the purposes of this video we'll be treating the acceleration into hyperdrive as near speed of light travel, because trying to explain hyperdrive and hyperspace in full would A, be its own separate video, and B, kinda breaks the laws of physics in multiple ways that I don't want to deal with right now. So Holdo manages to slice through a mega-class star dreadnought using the resistance ship the Radus. Would it really slice through it? Or should the question be, would it only slice through it? So the first problem we have to solve is the Radus's mass. We know its dimensions being nearly 3.5 kilometers long, and a volume of 1.121 billion cubic meters. Therefore, to find the mass, all we need now is the density. For some reason, the Radus doesn't have a cannon density, so we'll have to find the best real-life equivalent possible. For this, I've found two approaches.
Option 1.
We use a battleship. The heaviest class of battleship ever created was the Yamato-class Japanese battleships created in World War II, which, by looking at the water that they displaced, had a density of 644 kilograms per cubic meter. This would give the Radus a mass of 722.2 billion kilograms.
Option 2.
We look at the International Space Station. Using its mass and total pressurized area, we get a slightly over-calculated density of 458 kilograms per cubic meter, which gives the Radus a mass of 513 billion kilograms. For this video, we'll use the ISS comparison with the smaller mass of 513 billion kilograms, as this seems most appropriate for a spaceship. The next problem to solve is how fast was the Radus going? The short answer is I have no idea. Hyperspace travel has no real workable explanation, and obviously doesn't even remotely exist in real life. The best I can do is assume the ship is travelling somewhere near the speed of light, so I'll use a few different speeds and see what happens. The thing is, when you consider things moving close to the speed of light, physics gets really weird really fast. It's time to talk special relativity. That's right, this one's a physics lesson. Don't worry, I'll only explain what we need to know for this problem, and I'm not going to do any derivations or history lessons, so no need to panic and start taking notes. The first thing we'll need to discuss is the Lorentz factor, represented by the Greek letter gamma. This factor pops up all over the place in special relativity, and is calculated using the speed that the object is travelling at. So when an object is stationary, gamma equals 1, and for non-relativistic speed, so anything you'll encounter in day-to-day life, gamma is still pretty much equal to 1. As you approach the speed of light, gamma tends to infinity. But where is the Lorentz factor used? For the purposes of this video, we use it when considering mass. As objects go faster, their mass increases, and we use the Lorentz factor to calculate how much it increases by. The relativistic mass is equal to the rest mass multiplied by the Lorentz factor. There's a few things we're going to calculate. First is the kinetic energy of the Radus. Normally kinetic energy is equal to half times mass times velocity squared, but here we're using the relativistic mass, so kinetic energy is half times the Lorentz factor times by the rest mass, as we'll now call it, times by the velocity squared. This means at non-relativistic speed the equation is unchanged as gamma is equal to 1. Next is momentum. Same method applies. Mass times velocity becomes gamma times rest mass times velocity. The final two equations we'll need for now are deceleration force is equal to the initial kinetic energy divided by the distance over which the force is applied to bring the object to rest, and pressure equals force divided by area over which the force is applied. Now that I've got all the maths out of the way, I can actually explain what all that really means. So the biggest problem with figuring out everything going on here is we have no idea how fast the Radus is actually going. As I said earlier, we can treat the acceleration to hyperdrive as near the speed of light travel. even that is a very broad statement. So I'm going to take 4 different approaches to this. So the first approach is looking for a minimum possible speed by looking at how far the radius appears to travel in one frame. Watching the scene in 24 FPS, the radius travels at least the length of the Mega-class star Dreadnought within one frame. That means the slowest the radius could be travelling is 31,200 meters per second. At this speed, the Lorentz factor would still be 1, but the kinetic energy of the radius would be 250 quintillion joules. To put that into perspective, that's enough energy to meet the Earth's current demands for about 3 years. Figuring out how much of that energy goes into an explosion is difficult to accurately determine, but as it doesn't seem to be anything major moving post-collision, the number is likely very high. So we're going to consider a scenario in which 100% of the kinetic energy becomes explosive energy. The largest man-made explosion ever came from the Tsar bomber in Russia in 1961. That had a blast yield of about 210 petajoules. So that would mean that even this minimum possible speed, we would still have an explosion equivalent to 1,190 of the biggest bomb humans have ever made. So approach 2 will use 1% of the speed of light. Now we're getting into some actual relativistic speeds. 1% of the speed of light is around 3 million meters per second, and have a Lorentz factor of 1.00005. The kinetic energy of the radius would now be 2.31 septillion joules, which would power humanity for 28,700 years. The explosion given out by this would be the same as 11 million Tsar bombers. So approach number 3, we go to half the speed of light. The Lorentz factor is now up to 1.15, meaning that the mass of the radius would now be 15% bigger at 593 billion kilograms. The kinetic energy of the radius would now be equivalent to 31.7 billion Tsar bombers, enough energy to meet humanity's needs for 82.9 million years, or about 276 times longer than humans have even existed. So the fastest speed we'll consider for now is 99% of the speed of light. Here the Lorentz factor becomes 7.09, giving the radius a mass of 3.64 trillion kilograms. Its kinetic energy would be 160 octillion joules, enough energy to power humanity for 2 billion years, or nearly as much energy as the sun gives out every 7 minutes. The explosion from this would be equivalent to 763 billion Tsar bombers being detonated simultaneously. One thing we wanted to check was whether the radius could actually slice through the Dreadnought. The Dreadnought hull is made from Durasteel, with its nearest real-life equivalent being regular old steel. To pierce steel, a pressure of around 276 million pascals is needed. The force the radius exerts on the Dreadnought, even at its slowest possible speed, would be 19.2 quadrillion newtons. So now all we need is the surface area this acts over. The radius is somewhat bullet-shaped and is therefore well designed for slicing through things, but the only measurement we have for it is the maximum width. Even if we use this to calculate an absolute minimum value for the pressure, we find that even at its slowest possible speed, the pressure exerted by the radius is 58.9 billion pascals, over 200 times more than is needed to pierce steel. So slicing through the Dreadnought is actually the easiest part. Now we have some energies. What does that actually mean? We're comparing all this to the Tsar bomber in 1961, which had a yield equivalent to 50 megatons of TNT. But what does an explosion of that size actually look like? So using the website nuclearsecrecy.com/nukemap, we can simulate the effect of different sized nuclear explosions. Plotting a 50 megaton explosion on the surface of the Earth, we see that anything within a 6.01 kilometer radius of the explosion will be completely vaporized. Varying levels of blast damage would occur up to 43.4 kilometers away from the explosion, with third-degree burns occurring up to 51.4 kilometers away. The problem we run into now is that the website is only able to simulate explosions up to 100 megatons of TNT, the largest bomb ever designed by the USSR. Our smallest explosion is just shy of 60,000 megatons, and our largest is nearly 40 trillion megatons. So to estimate a blast radius, we need to extrapolate the data, which always creates a ton of uncertainty, and the further away from the real data you go, the worse the estimate becomes. Bearing that in mind, for our smallest explosion, one method of extrapolating the data would give a fireball radius of just under 60 kilometers, and an overall blast damage radius of around 325 kilometers. For the largest estimated explosion, we get a fireball radius of around 1,865 kilometers, and a blast radius of just over 9,000 kilometers. That's a fireball so large, if detonated in the right spot, it could vaporize most of mainland Europe, or most of the continental US, along with multiple Canadian cities and part of northern Mexico. Bear in mind, the Dreadnought only has a width of 60 kilometers. Now, I say only like a 60 kilometer wide spaceship is nothing special, But when it's only 60 kilometers in width total, that means that in our theoretical explosion, the entire thing is getting completely vaporized, not just sliced through. Everyone on that ship is dead. Rey is dead. Kylo Ren is dead. Finn is dead. Rose is dead. Phasma's dead for about a fifth time at this point. Remember though, that this is based on an overly simplistic extrapolation. The blast radius could possibly be even larger than this. So for as much as this uses extrapolations and estimations to come to the conclusion, I still think that it's very clear to me that the guys over at Lucasfilm horribly underestimated the maneuver that they created. That shouldn't just be it's sliced through the ship. That is a collision of ridiculously explosive proportions. But as per usual, to sit here and go, oh, you got the physics wrong, therefore it's stupid, misses the entire point of films, which isn't to get physics right, it's to tell interesting stories, and in a lot of cases, do cool things. And in this situation, the Holdo Manoeuvre very much comes under cool things. It is, without doubt, one of the most awesome parts of Star Wars that there has ever been. If you don't think that, you're not trying to watch this to have fun. You're watching these films to find something to complain about, which I know is very rich coming from the guy who has just sat here and tried to point out that the physics is wrong. But that's different. I can point out that physics is wrong while still enjoying the film, while still pointing out how awesome things are. And for much as, yes, that should have been Admiral Akbar's scene, I stand by that. I stand by literally everything I said in that other video. If you haven't seen it, go watch it. You don't get me ranting like this, unfortunately. It was text-to-speech voice. But the Holdo Manoeuvre is one of the most visually spectacular things, not just in Star Wars, in cinema, at least that I've ever seen. Does the seemingly somewhat inaccurate physics take away from it at all? Not in my opinion, because Star Wars has always been fantasy rather than science fiction, really. You know, they can write it off as hyperspace has weird rules, because, like I said, we can't actually explain what hyperspace is. I'm sure there are explanations somewhere, but again, it's not really based as much on science as it is on it being fantasy. It just happens to be set in space with spaceships. Everyone's mind immediately goes to, oh, this is science fiction. No, it's space wizards. It's just wizards in space with laser swords. And it's awesome, but it doesn't make it science fiction. Going in and complaining that the science doesn't always line up in Star Wars is like going in and complaining that the magic doesn't work properly in Harry Potter. Oh wait, I did that multiple times. Obviously, sometimes I like to come up with ways in which you can incorporate accurate physics while still keeping it working with the plot. In this case, I don't think that really works. Either you have to tone down the Holdo Manoeuvre way too much for it to still have the same impact it has, or you have to do way more damage than you could realistically explain away. Like, you can't vaporize all your main characters and still have the plot work. So in this situation, you have to leave it down to it's fantasy. Let it be. So was it scientifically accurate? No. Did that really matter in the end for the plot? No. Is Admiral Akbar dead? No, I'm refusing to admit it.